Okay, let's go through the main ideas of section 1.1 of your first chapter. We introduce the concept of a number line, which is just a straight line, and you take some point and call it the origin, which is 0, and then you mark off equal lengths to the right and call them the numbers 1, 2, and 3, and so on, and you can see that you can go all the way till infinity. So these set of numbers are called the natural numbers, and we can write them as a set 1, 2, 3, all the way till infinity. And now you can also add the numbers to the left of the origin, which are these numbers, and also you can include 0 in the set of natural numbers. So there are symbols for all of these, and when you add 0 to the natural numbers, you call them the whole numbers, though this notation is now not very common in the mathematics literature. So 0 union the natural numbers can be called the whole numbers. Now in any case, it's very clear that there are infinite natural numbers and infinite whole numbers. Now once you add all the negative numbers, then we call this set as a set of all integers, and we can write them like this. It starts from minus infinity and then it crosses over to the positive natural numbers, and then it can go all the way to infinity on the right hand side, and this set is called the set of integers and natural numbers and whole numbers, and all of them are infinite sets. So now the next important question is, what happens to lengths which are fractions? Okay, so this forms another set of important numbers, and we call them the rationals. So here there are examples of half, 3 by 4, and also a negative fraction. So these fractions are not included in the previous set of numbers that we have written, and so they deserve a very special name. This symbol is Q, and Q is the set of all fractions, and this is called rational numbers. And now we'll spend the next few minutes discussing a very important property of rational numbers. But before that, we note that Q implies that the number x, if it belongs to Q, can be written as a fraction, where you can write it as p by q, where p is itself an element of the natural integers, and q itself belongs to the set of integers, but you can't include 0, and this is a very stylish way of writing that you don't want q to be 0. Now it is often nice to cancel off any common factors between p and q, and before you write the rational number x. And one way, okay, let's, instead of x, I think r is a better symbol. So if you write the rational number, so r, can I just write it as r belongs to the set of all rational numbers, and r can be written as p by q, and it's often nice to make sure that the common factors are cancelled, and the way to write it, once again very stylishly, is to write that the common factor between p and q is equal to 1. Right. So now in the next page, there is a very interesting problem that is solved um, in the book, and since this is so important, I'm going to solve this in both the ways. There are two ways of solving this problem, and both are very interesting ways of solving this problem. But having solved the problem, we reach a very interesting conclusion about rational numbers, and that will be the end of the chapter. So let me first solve the problem. Here the problem says that there is a number line, and there are numbers 1 and 2 which are marked on the number line, and now he wants us to insert five rational numbers between 1 and 2. Now 1 itself can be considered as a rational number, so 1 does belong to the rational numbers because we can write 1 is equal to 1 by 1, and similarly 2 also belongs to the rational numbers because 2 can be written as 2 upon 1. Now in between these two rational numbers, can you insert 5 rational numbers? So I want to make it clear up front that 5, there's nothing special about 5. We can use the same method that we're going to learn here to input as many numbers, rational numbers in between 1 and 2 as we like. But anyway, here's the first method. So the first method is that consider a number which is exactly between 1 and 2. Now to find the number exactly between 1 and 2, you take the average of 1 and 2. And the way to take the average of 1 and 2, r is equal to, okay, let me write it as r1 is equal to the average, that is 1 plus 2 divided by 2, and this turns out to be equal to 3 over 2. So this number, which is exactly in between 3 by 2, is definitely a rational number, and we have managed to put one rational number in between 1 and 2. Now shall we repeat the process? The whole point of this example is that you can repeat this simple idea one more time, and this time we'll get a number between 1 and 3 by 2, and we'll get another number between 3 by 2 and 2. So let's just give them some names. Let me call this R1, let me call this R2, let me call this R3, and already we are doing very well. And we'll use the same idea for R2. R2 is equal to 1 plus R1 by 2, which is equal to 1 plus 3 by 2 divided by 2, and this turns out to be 5 by 4. And similarly R3 is equal to 3 by 2 plus 2 divided by 2, and this is equal to, how much is it, 4 plus 3, 7 over 4. So now we have three rational numbers between 1 and 2, and now let's do this idea one more time and look for a number here and a number here. Okay, so this we can call it as R4, and then this number we can call it as R5, and we have solved the problem. So we'll use the same idea again. R4 is equal to R1 plus R2 divided by 2, which happens to be 5 by 4 plus R2 is 5 by 4 plus 3 by 2 divided by 2, and this happens to be 5 plus 6, 11 by 4, 11 by 8, right? And let me just do R5 as well. R5 is equal to R1 plus R3 divided by 2. So R1 is 3 by 2 plus R3 is 7 by 4, the whole thing divided by 2, and this happens to be 6 plus 7, that's 13 by 8. Right? So this is the way the problem has been solved in your book. It's very interesting. So the main take-home message from this is you can add as many rationals, given any two rationals, you can add as many rationals in between as you like using this method. So should we just write it down in the form of a sentence, or maybe we'll write it down in the end. Okay, now here's another way in which you can approach the same problem. So let's do this. Same problem again. So I have a number line, and then I have 0, and then I have 1, and then I have 2, and I have to put in 5 numbers, 5 rational numbers in between this is just 4, I think one more, 5 rational numbers between 1 and 2. And in this time I'm going to actually, this is not well drawn, but I'm going to actually put them equidistant. Here's a very simple way in which I can put as many equidistant rational numbers in between 1 and 2. So the first step is write 1 as first of all, okay, 5. I want 5 numbers. So what you do is you add 1 to 5 and make it 6. And write 1 as 6 by 6. And write 2 as 12 by 6. So you can quickly see why we have chosen 6, because now very clearly 6 by 6 is strictly less than 7 by 6, is strictly less than 8 by 6, is strictly less than 9 by 6, is strictly less than 10 by 6, is strictly less than 11 by 6, and is strictly less than 12 by 6, which happens to be 2. So all of these numbers are rationals because they are all fractions. They can be written down as fractions, and as you can see that there are 5 of them. Let me just call them R1, R2, R3, R4, R5, and this time we've actually managed to make them equidistant. Now in both the examples you have to realize that there's nothing special about 5, so you can put as many as you like. And let's summarize this statement like this. An important property of rational numbers that we will take home: in between any two rationals we can have infinite number of more rational numbers. Okay, now the last part, the next section talks about there also exist numbers which are not rational, and so the next topic is going to be irrational numbers, and these are numbers on the number line that are not rational, and any number which is not rational will be called irrational. So let's stop this lesson now, and please go ahead and do the exercises of this chapter, and we will cover each topic in pretty much the same way. I should try and stop the recording now. So stop desktop and